Okay, so we'd like to investigate the RC circuit that we had here. And I'm going to draw that circuit with a power supply and a capacitor. And in this circuit, I've taken out the LED. The LED would normally be right here in between the two, with current flowing this way. The LED, because it tends to have a constant voltage drop or nearly constant voltage drop across it, is going to be irrelevant for our purposes. So I'm going to just simply take the LED out of the circuit. And we're going to use Kirchhoff's law to analyze this thing. So you can see that there's going to be a single current I through the circuit. And as I go around the loop, then I have the sum of voltages around the loop is going to be V, then it's going to be minus the current times the resistance, which is the voltage drop across the resistor, minus the voltage drop across the capacitor, which is going to be Q is equal to CV, and therefore V is equal to Q over C. And all of that is equal to 0. Well, let's write this in a slightly more friendly form as IR plus Q over C is equal to the voltage V. So this is our equation for the RC series circuit, but it's just Kirchhoff's law. Now, what I'd like to do is to analyze this equation in two ways. First of all, I want to give a qualitative analysis, and this qualitative analysis is going to give us the basic understanding of what's happening here in physical terms. And then, having done that qualitative and physics analysis, we're going to come back and I'm going to point you in the direction of a mathematical analysis which will make sense to people that have had calculus. And for the rest of you, we'll just kind of wave our hands and say approve. All right. Here is the important thing about the RC series circuit. And that is that the current that we have through the resistor is the rate at which the charge changes in the capacitor. Let's understand this in terms of water as an analogy. If the resistor is like a pipe carrying water, and the capacitor is like a tank holding a certain amount of water, then the amount of current flowing through this resistor is going to be the rate at which the capacitor fills up. So that the faster the current flows, the quicker the capacitor fills up. That's our basic principle. The higher the I, then the faster that the capacitor fills up. And also, when the capacitor is completely full, when its voltage is exactly equal to V, then the current will stop flowing altogether.
So I is equal to Q over C.
Hang on 1 second. So, when the voltage across the capacitor, which is Q over C, when that is exactly equal to V right here, then my I will drop to 0, and we're done. What was your question?
So I is equal to Q over C, or it's the rate at which?
Yes, I is the rate at which the charge is flowing. And when I do the calculus in just a minute, then we'll make that explicit. Okay? So these are the two principles that we want to use here. The I, we can think of the I as the rate at which charge flows. And so the higher the I, the faster C fills up. And then when C is completely full, that is when VC is equal to V, then my I trickles down to 0, and we stop filling up. So if you think about the capacitor like a tank, when the tank is full, we're done. Okay? Now let's actually take these two principles right here and see if we can draw ourselves a graph of the voltage across the capacitor as a function of time. We're going to examine the voltage drop across the capacitor VC right here as measured by a voltmeter, which is what we did in the video of our experiment. Okay? When you measure that voltage drop across the capacitor, assuming that it is initially uncharged, my capacitor is completely empty, and because my capacitor is completely empty, current is going to flow quickly, and my capacitor will start filling quickly. But as the capacitor gets more full, that is going to reduce the current flow, and so my capacitor will charge at a lesser rate of change. This is what we observed, how initially the capacitor's voltage went up by 0.04 volts every cycle, and it finally trickled off to 0.01 every cycle, and then the cycles got fewer and fewer between. And as the capacitor continues to get full, the rate of change will continue to decrease. So we have a decreasing rate of change, or concave down curve. And it will hit its limiting value of V right here like that. This is a description, a mathematical description of the voltage across the capacitor derived from these two principles. Now what we'd like to do is we'd like to make this a little bit more quantitative, because we'd like to have an idea of how quickly does this capacitor fill up. So I'm going to do this in two stages. First of all, I'm going to introduce some calculus ideas. I'll do the calculus ideas in red, so that if calculus is not your thing, you can just kind of stick your fingers in your ears and go la la la. But once we're done, we're going to take and get an algebraic result from this, and I'll do that in green, and you can unplug your ears at that time. So here's our calculus analysis of the RC series circuit. And just to be clear, the circuit that I'm talking about is one where we have an R and a C and a V like this. We start with Kirchhoff's law. We have a single current going through this circuit. And if I apply Kirchhoff's law to get sum of voltages equals 0, then I have V minus VR minus VC equals 0. Or in other words, at all times, VR plus VC add up to the whole power supply. And now VR is going to be I times R. VC is going to be Q over C, like this. And if it's okay with you, I'm going to write this as R times I plus 1 over C minus Q. Now comes the calculus magic, because in calculus terms, I is the rate at which charge is flowing. It is dq dt. And so what I have now is a differential equation. And this differential equation, if I'm really clever, can be made into a separable differential equation by subtracting 1 over CQ from both sides. And now I can multiply both sides by dt, divide both sides by V minus 1 over CQ. And get this right here. After doing the necessary integrals, eventually I end up with this relationship right here, that the voltage across the capacitor is going to be equal to V times 1 minus e to the negative t over RC. Eventually.
So are we trying to find the time changes here Q to Q
Yes, exactly. What we're trying to do is to really predict how long is it going to take for the capacitor to fill up. Okay? Now, here's where we're going to get out of calculus mode, and I'm going to present this equation algebraically here. So, if we wave our hands, poof, calculus, what we get is this equation here. And this is an exponential equation that describes the growth of the charge in the capacitor over time. And when I graph it, then what I get is exactly the shape of curve that we predicted right here, with a horizontal asymptote v as t goes out to infinity. So the limit as t goes to infinity of v times 1 minus e to the negative t over rc is equal to the limit as t goes to infinity of v times 1, because this quantity e to the negative t over rc goes to 0. And so I get v as my limiting value, my horizontal asymptote right here. Okay? So that's the first thing, is the horizontal asymptote. The second thing is that this quantity right here, Rc, is called the time constant for the circuit. And if I don't want to mess with doing fancy exponential calculations, and electrical engineers really like to be able to do stuff in their heads, then, actually let me give us a symbol for this. We're going to call this tau. The time constant tau, Rc, which is measured in seconds, is going to give us a rough indication of how quickly this circuit fills up. Unrelated to torque, yes. Unrelated to torque. If I take a look at the graph right here, then Rc, which is measured in seconds, can be plotted along the graph about like this. And what you can observe from this graph here is that after one time constant, my capacitor is kind of full. After 3 time constants, it's pretty full, and after 4 time constants, it's basically full. This is the 4RC rule. After 4 time constants, the capacitor is going to be 99% full. And to see that algebraically, let's imagine plugging in t equals 4RC into our equation. Since Vc is equal to V times 1 minus e to the negative t over Rc, if I plug in t equals 4Rc, no matter what R and C are, then I get some delightful cancellations. And I get 1 minus e to the negative 4 times V. And if I evaluate that on the calculator, takes me a moment to do this. Get the calculator up. There it is. Then 1 minus e to the, which is directly over the ln button, negative 4, is going to be 0.982. So it's actually 98%. We'll limit this to 98%. So that's the rough and ready rule that electrical engineers use for themselves, that after 4 time constants, our capacitor is 98%. I said 99, that's actually a mistake. How would we do this algebraically the long way? For example, I might ask this kind of a question. Let's put some numbers to this to see what's going on. Say I have a 10-volt power supply, and let's say I have a 1 kilo-ohm resistor hooked up to maybe a 1,000 microfarad capacitor. And the usual setup here for this circuit is that we are going to have a switch, exactly right. And at time t equals 0, we are going to flip the switch here, and we're going to allow the circuit to charge. Now that assumes the capacitor is initially uncharged, and in all of these problems we usually make that assumption. So our typical assumptions are that at t equals 0, the voltage drop across the capacitor is 0, and we're also going to assume that at t equals 0, the switch is grounded, so that at time t equals 0, our circuit goes into connected mode right here, and now current begins to flow through the resistor and down into the capacitor. So let's, with these assumptions in mind, let's ask two questions. Number one is, how long for the capacitor to become 50% full Next question, how long for the capacitor to become 98% full? And how the last question is, how long for the capacitor to become 100% full? It turns out that these three questions we're going to answer in slightly different ways here. The middle question is the easiest because this 98% is our magic number, which is the 4-time constant number right there. So, for the middle question right here, we're going to appeal to our 4RC rule. And the time constant is going to be the time constant itself is going to be 1 kiloohm, 1,000 ohms, times 1,000 microfarads, and 1,000 times 1,000 is 10 to the 6, times 10 to the minus 6 is going to be 1, and an ohm times a farad, believe it or not, is seconds. Why is that? Well, because an ohm is equal to a volt divided by an amp. Which is a volt per coulomb per second. And a farad is equal to a coulomb per volt. And so when you cancel out all your units and recognize that 1/1 seconds is seconds, you see that sort of magically ohms times farads gives you seconds. So what I get is then 4 seconds for my 4RC. It's going to take 4 seconds for my capacitor to become 98% full. All right, now let's tackle the second question here. How long for the capacitor to become 50% full? Because this is not my magic 98% number, I'm going to need to solve an exponential. The capacitor is going to become 50% full when its voltage is 50% of the power supply's voltage here. In other words, when VC is equal to 5 volts. And so if I set VC equals 5 volts, which is equal to then V times 1 minus e to the negative t over RC. Notice that t over RC is my time constant, and which we already calculated at 1 second. Then I have this equation right here. And I'm going to solve this equation by isolating the exponential and then using inverse functions. So I'm going to first divide by 10. That's equal to 1 minus e to the negative t over 1. And I'm going to isolate the exponential by subtracting 1 from both sides. And then multiplying both sides by negative 1. And now here, I've isolated my exponential. I'm going to take the natural log of both sides. And on the right-hand side, the natural log cancels the exponential and leaves me with negative t. On the left-hand side, I get ln of 0.5, which the calculator will tell me is negative 0.693. And so therefore, t is equal to 0.693 seconds. Special value is negative natural log 2, and natural log 2 is a common value. Yep. Now, I want you to observe the nonlinear nature of this whole thing. Looking at my curve here, it only takes me 0.693 seconds to fill up my capacitor halfway. But it takes me a full 4 seconds way out here to fill up my capacitor to 98% or 9.8 volts. Now, for the third question, how long does it take to fill up my capacitor 100%? From the graph, you can see that the capacitor will continue to fill at an ever-decreasing rate, approaching the final voltage of 10, but never getting there. It takes an infinite amount of time to go that last 0.2 volts. And so the answer to our third question, how long for the capacitor to become 100% full? Infinity. Now, in a real live RC circuit, at some point we just say full enough. And full enough for most purposes is 98% full. If I wanted 99.9% full, then I could set that equal to, then I could set the voltage equal to 99.9% out of the final voltage and solve. And as I do, each additional percent or 0.1% will take longer and longer and longer to achieve. That's the basic RC circuit. And with that in mind, are there any other questions? I think those